Hi everyone, my name is Pravish Krishna and my student ID is 101538718, and this is my walkthrough for assignment 4. The goal here was to build an image classifier on CFAR10, deliberately overfitted, and then show how different regularization techniques pull out the validation curve back up. I'll walk through three models: a dense baseline that overfits the same model with L1, L2, and dropout regularization, and finally a small CNN with the data augmentation. First, we have the imports, and I will switch to data preparation. So we can see here I'm using CFAR10. It's 60,000 color images, images, 32 by 32 pixels across the 10 classes like airplanes, cat, uh, ship, and truck. Keras gives us it to pre-split into 50,000 train and 10,000 test, two pre-processing steps, and two pre-processing steps. I scale the pixel values from 0 to 255 down to 0 to 1, which keeps the gradient well behaved. And one hot encode the labels because I'm using categorical cross entropy as the loss. For the train validation test splits, the CFAR10 already gives me a train and test set, but I need a separate validation set to actually see overfitting while training. So I peel off 20% of the training data as validation, strip it so every class is represented evenly. The test set stays untouched until very end. So we come to the baseline. With the first model, intentionally it is bad. It's fully connected network, flattened to 1024, and then 512 units. Then the 10 class softmax. That's several million parameters feeding of only 40,000 training images with zero regularization. So you can see what happens in here. You can see what happened in the loss plot. The training loss keeps dropping, but the validation loss bottoms up around and epoch 5 and 6, then climbs. The accuracy plot shows the same story uh, here as well in the accuracy spot. So so uh, so the training accuracy keeps rising while validation flattens, and the gap between the two curves right here, the gap between the two curves is overfitting. The model is memorizing the training set instead of learning patterns that generalize. So same architecture, but I now add three things: L1 and L2 weight decay on dense layers that penalizes large weights, so the model can't lean too hard on any single feature, and dropout set to 0.5 between layers, which randomly zeroes out the half of the activations during training, so the network can't rely on the specific neuron. The result is visible in the curves. Training accuracy is actually a bit lower than the baseline, but validation accuracy is higher, and the gap between the two is much smaller. That's the trade-off you want. Sacrifice some training fit to get real generalization. We can see that here. Now we come to convent with data augmentation. The third model is proper convolution network. Dense layers ignore the spatial structure of an image. They see a flat vector. Convolution slides small fillers across the image and share weights, which is the right inductive bias for vision. On top of that, I added a data augmentation block at the input, random horizontal flips, small rotations, and small zooms. Every training batch sees a slightly different version of each image. So it's like having a much larger, bigger training setup for free. I also kept the dropout and a bit of L2 inside the network. The CNN beats both dense model and test accuracy, and the train validation curve stays close together for full 25 epochs. Final evaluation and epoch discussion. So, uh, on the held out test set by the over parameterized baseline lands around the low 40s in accuracy, the regularized dense model is several points higher and CNN with augmentation is clear winner. On the question of how many epochs you actually needed, the baseline peaks around epoch 5 or 6 and get worse after that, so more epochs hurt. The regularized model keeps improving for 15 to 20 epochs. The CNN was still slowly improving at 25 epochs, so it could go longer with early stopping, watching, and validation loss. So the takeaway, uh, a big unregularized model overfits fast on dataset like CFAR10, L1, L2, and dropout cut the train validation gap meaningfully, and switching a convent with data augmentation gives you biggest single jump in accuracy because you are finally using a model that matches the structure of the data. Thanks for watching, and this is Pravesh Resta.